All right, well, good morning, everyone. Depending on when you're watching this, it's about 7 o'clock in the morning on Friday, and I'm hoping at this point we've had a pretty good first week, so I'll kind of save a lot of the extra commentary here because I think we're in a good groove right now. All right, so for this video, we're going to try to make these a little shorter. We'll see what happens. There may be some problems from problem set 1 that you're going to want to revisit, make sure you did properly, just like lecture always. Sometimes I don't get far enough, so maybe you'll have to go back and take a look at some of those problems again. In this video, this particular one, you should be able to look at problem set number 2, numbers 1 through 3 after this short video. Section 13.2 is where this video and probably the next one will apply, so that's a really good section to read. And then you definitely want the chapter 13 slides from D2L. So if you want to stop the video and kind of get organized so you sort of have all that stuff, or better yet, look over section 13.2, kind of get your head back in the game and go to the slides and maybe copy down example number 1 and 2 from the chapter 13 slides, because that's where we're going to kind of get started today. I'm not going to rewrite all of that, but you should have those right in front of you. So let's go. Okay. So this is the same heading from the notes, and I already lost my marker. Ah, there it is. Sorry, left it over here. And the last really long-winded video talked about two ratios that mathematically look very similar. Q and K. Remember, it's products, final state, divided by reactants, initial state, and it's concentrations raised to the power of the coefficients. Now that kind of looks like kinetics in order of reaction, where we didn't just take the coefficients, put them as power. In equilibrium, that's exactly what we do. We balance the equation and use the coefficients as powers. Q is non-equilibrium, K is equilibrium, and then we know how the reaction has to shift based on the value of Q and K, but that's the example we're going to do right now. Okay, so the first example number 1, I'm over here on my slides. All right, so we're doing the Haber-Bosch process again. And you're given a K value, but it has a subscript P, which I didn't explain very well last time. So this is example 1. And it's the same thing we're doing, we've done many, many times. In equilibrium with. Okay, now I'm going to show you some math later. It's actually not that hard. These are gases. So we don't have to measure gases in terms of concentration, moles per liter. That's typically for an aqueous solution. We could also use pressure, because the partial pressure of nitrogen, the partial pressure of hydrogen, and the partial pressure of ammonia, from gas laws if you remember, are really substitute measurements for concentration. So we can use pressure or concentration to do this. So, but first things first, and the first thing says, write the appropriate Kc expression. So if we were going to do this in terms of Kc, concentration, that's what that means, molarity. We would do, let's see, it's products, so we take the ammonia concentration squared divided by the hydrogen concentration cubed times the nitrogen concentration to the first power, which I'm not going to write. And that would be the Kc expression. We could also use pressures. So it would be the partial pressure of ammonia squared over the partial pressure of hydrogen cubed and the partial pressure of nitrogen. So either one of those would work. And in this problem, you're given the value. Now typically what we would do is you'd be either given a value or given the information to calculate a K or a Kp. So in this problem, you've been given the fact that this has a handbook value, and it's 4.34 times 10 to the minus third. Don't worry really about the number right now. And the units are kind of interesting. The units here, if you're going to use millimeters of mercury, so it'll be millimeters of mercury squared over millimeters of mercury to the 4th power. So cubed. So the units here are actually going to be millimeters of mercury to the -2 power. That squared is going to be down here. So it's kind of a strange looking unit, but it makes sense. And I'm not going to worry too much about the units there. Okay. So that's part A for this problem. An experiment yields partial pressures of hydrogen, nitrogen, and ammonia, and you're given the values there. Calculate Q. Okay, yeah, we don't know if this is equilibrium or not. So in part B, you're not told that it's equilibrium, so we don't know. So we're going to calculate Q. And what are we given? We're given pressures. And I'm just going to make these substitutions. Go over to my notes here. And let's see, we're told that the ammonia is 345 millimeters of mercury, but we have to square that over 125 millimeters of mercury cubed, and then 210 millimeters of mercury to the 1st power. So we're just taking actual numbers and putting it into here and solving this. So if you want to stop the video and see what you come up with, I came up with 2.9 times 10 to the -4th. Again, the units we know have to be millimeters of mercury to the -2 if you work out all these units. So go convince yourself that that's what it is. All right. So that's part B, just calculate that. And part C says, is the reaction at equilibrium? So I'll just put that over here, I guess. Well, no. The reaction's not at equilibrium. That's equilibrium. That is not equilibrium. These two are not the same number. So what would have to happen here? Well, okay, this is smaller than this. So Q is, well, let's see, how did we do this before? I think we always put the Q here. So QP is smaller than KP. Okay, so this is Le Chatelier's principle, the idea that equilibrium shift back and forth to reach equilibrium. Okay, well, if this is smaller, that means that the reactants are bigger than they should be, and the products are smaller than they should be. Yeah, okay. So, what does that mean? Shift right to reduce reactants and increase product. So specifically for this equilibrium, more ammonia would have to be produced, and you would have less nitrogen and hydrogen to push this reaction towards the right to reach equilibrium. So that's called a shift right, a forward shift, whatever you want to call it. Okay, so that's a good example of the Chatelier's. In terms of pressures, that means that the partial pressure of hydrogen and nitrogen will go down. The partial pressure of ammonia will go up. Okay. That's a good example. And that's one, and I'm also going to bring this term in later. This is called a homogeneous equilibrium. Because everything is a gas. Sometimes we're going to see things where some things are solid and the other things are aqueous, or some things are solid and some things are gaseous. And those are heterogeneous equilibrium. So I'm just kind of sneaking that term in there. Okay, so that's example number 1. And then, part D in the problem, if you're looking at the slides, is do the units make sense? Well, we went through that already. Okay, I'll give you a chance here for example number 2. And this is an example that is exactly out of the book because I thought it was a good example and I need some time here to set this up. So if you want to just take some time while I fumble around here and erase all of this or double check your notes or find this example in section 13.2, you'll see it. It's a table of data. It's just like lecturing. You have to watch me erase sometimes. I know it's very exciting. And I may not do this whole example on the video because I actually didn't write out the answers in my notes because I normally would have you do that. And that's fine, that's no problem. So I may just set this one up and have you repeat it from section 13.2. So this is example 2. And this really is from section 13.2. And what you're given, this is called the water-gas shift reaction, I think. Not that it's important. And it's it's a homogeneous equilibrium. So the chemical reaction is a little more complicated. It's carbon monoxide gas plus water vapor, so steam, in equilibrium with carbon dioxide gas and hydrogen gas. And there are 3 experiments that you're given here. And these are not necessarily equilibrium conditions. So you have, let's see here, 3 trials, 1, 2, and 3. So you'll do this 3 times. And then you're given, well, we don't know if they're equilibrium concentrations. We use brackets for equilibrium. We use parentheses for non-equilibrium. So I'm putting parentheses here. It looks kind of weird. It looks like it's kind of from a chemical formula, but we don't know. But there's still molarities. Okay, so you're given 3 trials where you're given concentrations of everything. So in trial 1, O2, O3, these are the same. Oh, and then these are the products over here. So these are 0.0040 and 0.0040. Okay, so this problem, I'm just gonna kind of set this up. I think you kind of get the point. Is these are just given values to you. So the basic idea for this is calculate your Q. In this case, it'll be a QC. Compare it to the K value. Oh, I'm sorry. You're given something here. You're given the fact that Kc equals 0.64. And it actually has no units, which makes sense because Kc is going to be, and this is balanced by the way, every coefficient is 1. So it's the concentration of carbon dioxide to the first power times the concentration of hydrogen to the first power divided by, okay, you get the idea. So the units cancel, so there are no units on this one. So I think this is a pretty easy problem, but that's just me. So the basic idea is calculate Q, find, compare it to K, and see where you are. So let's just do the first one together here. So for trial 1, QC, and I don't think I want to write out the expression with the symbols. It's just this to the first times this to the first. I think we can just go right to the numbers. So it's going to be 0.0040 molarity times 0.0040 molarity over 0.0203 molarity times 0.0203 molarity. So in these other trials, you'll set up the same thing. Just set up products over reactants. Compare the two. Now I didn't do this, so I just need a second here to do this on my calculator to make sure that we got that. And then the idea is what has to happen to go to equilibrium? Does it have to go this way or this way? Do these pressures go up? Or do these pressures go down? Do these pressures go up? Or do these pressures go down? But we're given molarities here, so it doesn't really matter what we're talking about. So, so this is 0.004, and that's really squared, isn't it? Well, I'll just do times 0.004 divided by the quantity 0.0203 times 0.0203 parentheses, and I got I think we're just going to take 2 sig figs. I think that's right. Double check if that's right. I think it is. Okay. I'm not probably going to take time to double check this. So if I got that wrong, you can correct this on here. So wow, what does that mean? So QC is a heck of a lot less. We can put bam. Wow, okay, so, well, first off, this is kind of interesting. Kc here is less than 1, which means that the products are favored. There's just more, they're there in more abundance than this, so the denominator just has to be bigger than the numerator. Okay, so that's good to note right away. So in this case, Q is a whole heck of a lot less than K. I mean, it's not even close. So we're really going to have to push this equilibrium to the right. Yeah, so we'll have to make the denominator a lot smaller. Yeah, okay, so you get the idea. So this is going to have to be a shift to the right to produce more CO2 and H2 and less of those two. It's basically the same thing as the last one, to shift right. So what you want to do is go through trials 2 and 3, do this same analysis, and see if it works, okay? So I think I'm going to keep going with this video to show you a relationship between Kc and Kp. It's not that difficult of a relationship, but I think I'll just show it to you right now and keep going. But if you want to stop the video, take a break, and do some of these problems, finish this problem off and check it with the book, that will be fine, okay? But let's just keep this going. All right, so I just need to erase this. I keep saying the videos are going to get shorter, but maybe not right away. Because this one I think makes sense. Yeah, and then in this problem, then one of the questions is, you want to figure out which of the 3 trials is closest to equilibrium. So which one closest matches, which Q is closest to the K. Okay, what I'm going to do, I'm still under part B here. Yeah, I'll just toss this in now. I'm going to toss a couple of things and then we'll stop. Because this stuff really isn't that mathematical. So I'm still under the notes. And this is homo and heterogeneous equilibria. If you set up your notes ahead of time, that'll actually be really helpful. So I'm just tossing this in there. So, and this one is kind of from problem set number 1, where you have a moderately soluble ionic compound. So, you might remember from first semester from doing metathesis reactions and solubility rules that compounds with lead tend to be solids, so they don't tend to dissolve very much. But you actually will have an equilibrium here with, in this case, it's lead with a +2 charge. You can figure that out. Okay. This is a heterogeneous equilibrium because you have a solid and then 2 aqueous phases. So here we do not So remember that. If you see a solid in equilibrium with aqueous or gases, do not include it in the K expression. Don't do it. So in this case, the K expression is really easy. It's K equals the concentration of lead times the concentration of chloride ions squared. There is actually no denominator. If you want to call it 1, go ahead and do that. And this is given a very special name, which we're going to come back to maybe. This is called a solubility product. It's a KSP. It basically tells you how much of the solid dissolves. If it's a big number, a lot of it dissolves. If it's a tiny number, which almost all of them are, that means not much of it dissolves at all. Or dissociates, I should say, is a better word. Let me show you a couple of other ones just kind of real quick. Another one that's possible, and this one's kind of weird. Calcium oxide is a form of lime or limestone. Okay? And that will react with carbon dioxide gas. And that will produce another, this is called slaked lime or something like that in geology. And then you get calcium carbonate from that. And that's a solid. Well, that's kind of weird because 2 of the 3 chemicals here you would not write in the equilibrium expression. So it's still heterogeneous. This is the only one you're going to write. It looks really strange. So Kc for this one is going to be, well, you don't write that. So that's nothing. So you have to put a 1 there as a placeholder. Product divided by rate, and you don't write that one. The only one you write is carbon dioxide, and I think this is balanced, so that's to the 1st power. That looks really weird, but that's what you would have to write for this expression. And then Kp would simply be 1 over the pressure of carbon dioxide gas. So that's actually a really simple expression, but it's kind of weird you're ignoring 2 of the 3 chemicals. And another one. Technically, this is also a heterogeneous. Heterogeneous just means different phases. So you have liquid water in equilibrium with gaseous water. So this would be vaporization and condensation, that equilibrium there. So do not include those when you write the K expression. Pure liquids. Pure liquids. Different from aqueous solutions, which are not pure. So pure liquids do not include. So your K here is going to be kind of weird looking. It's just a concentration of gaseous water, or excellent. So the math there, so we have homo and heterogeneous examples, and then we have calculating a Q and figuring out which direction the equilibrium goes. I was going to keep going, but I'm going to stop there, and then I'll pick up with the final set of equilibrium calculations here. So you can go ahead and take a look here, and this will be, boom, video number 1, equilibrium calculations.